We'll be looking at the vector equation of a line, and we will also looking at pairs of lines. So let's get started. Here's a line. Here's a known point on the line. I'm going to call that point A. Let's make this the origin. Here's another point on the line, R. Position vector of the point A is OA. I'll call that little a. Position vector of the point R, I'll call that little r. And I'm also going to draw a vector parallel to the line, and I'm going to call that vector, that free vector parallel to the line, I'm going to call it B. If A is the position vector of any known point on the line, R is the position vector of a general point on the line, on the line, and B is a free vector parallel to the line, and usually we refer to that as the direction vector for the line. Then define a quantity lambda. Lambda is a scalar variable, or also called a parameter. Then the vector equation of this line can be quoted as R. Actually, before I quote it, let me just prove it. I need to get to some general point in the line, starting from the origin. Starting from the origin, I need to get from O to R. An alternative route would be to go from O to A, the known point, and then from A to R. From O to R would be small r, little r. O to A would be little a. From A to R, if you think about it, from A to R, it's a vector, the vector AR. And that vector AR is parallel to this free vector that I have parallel to the line. And we all know that when two vectors are parallel, one can be written as a scalar or multiple of the other. Therefore, R is equal to A plus R is equal to A plus, the scalar is going to be lambda times B. This is a quotable expression, and it can be used to find the vector equation of a line. You must be very careful that you fully understand what each of the terms in that equation, what each term means. Let's do a simple example up front. Find the vector equation of the line. Find the vector equation of the line that passes through the point 1, 3, minus 2. And is parallel to the vector 2i plus 3j minus 5k. this one is kind of simple, because if you draw a line representative of what we're talking about, that is the point through which the line passes with coordinates 1, 3, -2. And they're saying that this line is parallel to a given vector. The given vector we're going to call B, and we're going to label it 2i plus 3j minus 5k. If we quote r equal a plus lambda b, the only two things we need to plug into this equation are the position vector of the known point and the free vector that's parallel to the line, or the direction vector for the line. So we have both. R can therefore be written as I plus 3j minus 2k plus lambda into 2i plus 3j minus 5k. Very simple. In column vector notation, column vector form, the equation of the line looks like r equals 1, 3 minus 2 plus lambda into 2, 3 minus 5. Get accustomed to both formats, because you will be using them interchangeably. Okay, let's try another example. Example number 2. Find the vector equation of the line that passes through and the points. Let's call the first one A, 1, 1, 3, and let's call the next one C, 2, minus 5, and 4. So let's run this one. Here's the line. Here are the 2 points. Let's call this one A, 1, 1, 3. Here's the second point. 2, minus 5, and 4. And we call this one C. Now, if we were to quote the vector equation of the line as being R is equal to A plus lambda B, remember again, we're only plugging in for the A and the B. A is defined as the position vector of any known point. Any known point. I repeat, any known point. Guess what? In this example, we have 2 known points. So you can close your eyes and pick either one to represent the A. Just so happens that the first one, we call it, the point is labeled capital A, so I'm going to use A to represent A. But you could just as easily have used C to represent A, because by definition, A is the position vector of any known point on the line. How about B? B is a free vector parallel to the line. Well, that vector could be on the line itself, and what we're going to use to represent the B is the vector from A to C. So I'm going to rewrite this equation as R is equal to A plus lambda, and the B will be the vector AC. So I'm going to plug in A for A and then AC to represent B. So obviously I need the vector AC, which would be OC minus OA. I'm going to use column vector notation here. OC is 2 minus 5, 4 minus OA, 1, 1, 3, to give me 2 minus 1 is 1, minus 5 minus 6, hope I could add. 4 minus 3 is 1. All right. And therefore, the vector equation of the line could have been written as, or could be written as, r is equal to a 1, 1, 3 plus lambda times 1 minus 6, 1. I could have just as easily written it as r is equal to 2 minus 5, 4 plus lambda into 1 minus 6, 1. So there. How you like them apples? All right, so it's easy to write down the vector equation of a line if you're given 2 points in the line, or if you're given 1 point and a free vector parallel to the line. That's what the first 2 examples were used for. Couple important points. If you look at the vector equation of a line, let's draw back the line here again. The vector equation of the line is given as r is equal to a plus lambda b. Well, if you were to make a comparison with the regular Cartesian equation of a line, y equal, let's say, 2x plus 5. If you think about it, every time you plug in a value of x, you get a corresponding value of y, and therefore an xy coordinate pair. Example, x equal 1, y is equal to 7. 1, 7 would therefore be an xy coordinate pair. So for every value of x, you get a corresponding value of y, and hence an xy coordinate pair. That's what the regular Cartesian equation of a line, that's the kind of information you can get from that. The vector equation of a line, for every value of lambda that you plug in, you end up with the position vector of a different point on that line. So let me demonstrate. This is my origin, and this is the A. This is the vector A. I'm not going to draw in the generic R. This is the vector A. Okay. So when lambda is equal to 0, if you plug it into the equation, you get R is equal to A. When lambda is equal to 1, R is equal to A plus B. Lambda equal 2, R equal A plus 2B. And so on down the line. Lambda equal minus 1, R is equal to A minus B. Every time you use a different value of lambda, you get the position vector for different point along the line. This one is A, this one is A plus B, this one is A plus 2B, A plus 3B, and so on and so on and so on. The one with A minus B might be back here somewhere, when lambda is minus 1. This one is A minus B. So this is lambda equals 0, lambda equal 1, lambda equal 2, lambda equal 3, lambda equal minus 1. Different values of lambda will give you the position vectors for different points along that line. So that's the one way you should think about the vector equation of a line. Okay. Well, that's pretty straightforward stuff. Now, the next part of what we're required to learn is we have to compare lines. Compare lines. Compare pairs of lines. Oh man, what's going on here? Line pairs. I'm going to just do one comparison in this tutorial. The next tutorial, save a second tutorial for that. That one is a little more lengthy. Okay, for lines in 3 dimensions, there are 3 possibilities. A, the lines are parallel and will never intersect. B, the lines are non-parallel and intersecting. And the third scenario, the lines are non-parallel and non-intersecting. Yeah, seems a little curious, but if you think about it, if you're in 3 dimensions, you don't always have to be in the same plane. And therefore, you can have lines that are not parallel to each other. You can have one directly above the other, and they never intersect. And they're not parallel either. So that's okay. The lines that are non-parallel and non-intersecting are called skew lines. S-K-E-W. Skew lines. In this tutorial, we're only going to look at parallel lines, and then, like I said, the other two, it takes a little bit more explanation. So I'm going to put that in a separate tutorial. So let's look at case A. I have 2 lines. How can I tell that they're parallel? Now remember, generally speaking, you don't have a diagram. They don't show you 2 lines in 3 dimensions, more or less. You would most likely have the vector equations for the 2 lines. And how do you use that? How do you use the 2 vector equations to show whether or not the lines are parallel? Well, the first line, let's say it's called R1, is equal to A1 plus lambda B1. B1 would obviously be the direction vector for that first line. B1, like that. Second line, I'll call this equation R2, is equal to A2 plus mu. B2, have to have a different parameter. Doesn't have to be the same. So the parameter in the second equation is mu. And the vector that's parallel to the second line, the free vector parallel to that second line, would be the vector B2. Well, guess what? Let's call this first line L1 and the second line L2. If the 2 lines are parallel, and they have direction vectors that are parallel to themselves, then the 2 direction vectors must also be parallel. That should kind of make sense. Just look at the diagram. If 2 lines are parallel, the direction vectors are parallel. And therefore, we know that when vectors are parallel, one vector can be written as a scalar multiple of the other. So that is your test. If the lines L1 and L2 are parallel, it implies that their direction vectors B1 and B2 are parallel, which implies that B1 can be written as some constant. Let's say just K times B2. If you can do that, then the 2 lines are parallel. So here is our first line pair. Determine whether or not the following pairs of lines are parallel or not. And here is the line pair. R1 is equal to I plus j plus 2k plus lambda into 3i minus 2j plus 4k. Oh, my. And then the second line, R2, is equal to 2i minus j plus 3k plus mu into minus 6i plus 4j minus 8k. So what we're going to do is we're going to isolate the b vectors, the direction vectors for each line. I'll call the first one. This is the direction vector for the first line. That's the direction vector for the second line. Let's call them b1 and b2 respectively. b1 is equal to 3i minus 2j plus 4k. b2 is equal to minus 6i plus 4j minus 8k. If from b2 I factor out a minus 2, what's left inside the brackets? That would be 3i minus 2j plus 4k. Let's double check. Minus 2 by 3 gives me back the minus 6. Minus 2 by minus 2 gives me back the 4. Minus 2 by 4 gives me back the minus 8. But if you look inside the brackets, that vector there is b1. Therefore, b2 can be written as minus 2 times b1, which implies that the lines are parallel. If their direction vectors are parallel, the lines themselves must be parallel.